So we're interested in creating some kind of a diagnostic statistic that tells us how good our model is doing. Especially, it would be good to be able to compare one model to another and say which one is better at explaining our data. So you can think, just in general, if I had a model of my Amazon thing. Let's imagine I have a model that's predicting the total dollar value of my basket of purchases. My predictions aren't going to be equal to the actual purchases. And so it's pretty straightforward to think, well, we ought to be tracking how far off our prediction was. So we talk about why. So why are our individual data points, and we'll talk about our predicted value. We'll call that y hat. So we've got y, the individual data, y hat, our prediction. The difference between y hat and y we'll call the error. And the idea behind having a good model then would be to say, well, maybe within some constraints, what's the smallest I can make the error? It turns out it's a lot easier to minimize the error squared for a lot of reasons. But first, if I'm off by $10 or if I'm off by negative $10, really I'm off by 10, so I don't really care about the sign of my error. I really just care about the error. So it'd be natural to think about taking the absolute value, and that's one way that you can do it. The math, and so when you square the error, it ends up being consistent with assuming that the errors themselves are normally distributed, which is often the case. And there you get some other nice mathematical things. So, and you can think, just in general, if I'm making the squared errors really small, I'm also making the normal errors small. I just happen to be putting a greater emphasis on observations that are really out of whack. So if you square the errors, it makes you pay more attention to things that are really wrong relative to just looking at the absolute error. And that's what we're going to do in linear regression. So we want to minimize that sum of squared errors. Right, I've got error for each observation. I could square it, and I'm going to add those up and minimize that sum. So if I minimize the sum of squared errors, I'm going to get the best possible model given my selection of independent variables. And that will constitute the least squares, the linear regression least squares estimate of the model. But I can, so the difference between y and y hat, that's my sum of squared errors, but I can also think about how much error I've explained. So what if I just started with a baseline model of just using the average? Obviously my model, the linear regression model, is going to do better than that. So if I look at y hat minus y average, or y bar I've written, but it's the average y, and square that, that's going to be the amount that I've explained using my model. So you can imagine maybe I get halfway there with my model, and then there's error up above that gets squared. And so I can take the difference between y and y average and split it up into the part I explained and the part I didn't. And naturally that means that the sum add up. So if I take the sum of squared error, so the part that I didn't explain, and add it to the sum of squares regression, or the sum of squares that I explained, it's going to add to the total error, sum of square total, which is the difference between the individual data and their average. So that's we don't even have a model, we're just going to use the average. Our model hopefully does a lot better than that, but maybe it only does a little better than that. So if I take the amount of error I'm explaining and divide by the amount of total error, well, we want that number to be big, right? It would be great if it was 1. That would mean we explained everything with our model. But let's say we didn't. What if we only explained half? Well, that quantity, sum of squared due to the regression divided by sum of squared totals, is called the R-squared. And it's telling us the fraction of the variance that we've explained using our model. If it's low, and that was my discussion before, so if you get 2%, you really don't have any clue what's going on for any individual observation. You can just talk in general about when this goes up, this goes down. You can talk about averages, but you can't talk about specifics. Where if you're explaining 90% of the total error, well, now you really can say a lot about what individual things are doing. So that R-square is just it's an expression of how good our model is doing overall at explaining the data. But we can look at the individual coefficients in our model. So in our Amazon example, the number of purchases and whether or not I bought a book, and that we can test those individually for statistical significance using a t-test. So it might be the case that the number of purchases is useful and the number of books is not useful enough that we're certain, that we're 95% certain that it is. So just like in Unit 1, we were doing t-tests for the difference between means, you can do a t-test that the coefficient is not 0 and read the critical value and look at the significance. And so that's what Excel reports in its regression statistics. So I have some data from 2009 annual statements for some public firms that I collected with my undergraduate statistics students. And we'll run a regression and try to predict the total, okay, so predict the debt levels of a firm given their size. So we'll assume that bigger firms have more debt and see if this turns out to be true.